Analysis of time series, chapter 8, smoothing in the time and frequency domains. So we're going to think more about how to estimate the trend in a non-parametric way, and that's called smoothing. And it turns out to be useful to look at smoothing in the behavior of your smoother in the frequency domain, and there's a closely related problem of seasonal adjustment that we'll look at. So we've seen smoothing in the context of estimating a spectral density from the periodogram. In general, you may have seen smoothers before. The general smoothing problem in the time series context is to estimate a non-parametric trend from a time series. It's very similar to scatterplot smoothing applications, where we also see smoothers. Now, when you view smoothers in the frequency domain, you expect a smoother to shrink high frequency components and preserve low frequency components. The idea here is that the low frequency component is probably the kind of trend that you want to study, and the high frequency component is the noise that you want to try to remove. We're going to motivate this development through a particular example looking at economic data. So the economy fluctuates between periods of expansion and periods of slower growth or contraction, recessions, for example. And we all know that these happen. And one of the signs of an economy not working as well as it should is high unemployment. Then labor is underutilized because lots of people who are willing and able to work are not working. And this leads to hardships for individuals and communities and inefficiency to economies. And so everybody, economists, politicians, business people, all of us have some interest in understanding fluctuations in unemployment in particular and the economy in general. So it seems that there are some kind of natural cycles. Historically, sometimes inflation, sometimes unemployment is going up and the economy is doing badly. Sometimes the shorter term booms, and this seems to be a natural part of the way markets work, the capitalist system. So maybe it's not a problem, but maybe it needs to be understood. And so one of the things people do to try to understand something is collect data on it. And the Bureau of Labor Statistics, BLS, collects monthly US unemployment figures, which is the main source people use to try and figure out what's going on. Of course, this is not a course in economics, so we're not going to try to get into the real subtleties of the situation, but we're going to look at the data as a time series. Here's some data extracted from the Bureau of Labor Statistics. This data is not seasonally adjusted. We're going to talk more about seasonal adjustment soon, but seasonal adjustment is something that the Bureau of Labor Statistics does to deal with the fact that there's some annual pattern on top of slower trends. So there's always extra employment in the summer and around Christmas. And okay, so the data come at us when we download them. They come at us as a CSV file, comma separated file in this format you can see here. This is just what happens when you read the data straight into R. You get something that looks like a matrix. Technically, it's going to be a data frame with columns for each month and the year. Now, so our first little coding exercise, little R exercise, is to turn this tabulated data into a time series. And there's different ways to do this, but just as a kind of R exercise, let's look through the code below and see how it works. So what we do here, little u1, turns the required columns of big U1 into a matrix and then transposes it. And then we set its dimension to null. So what's going on here? Let's bring up my pen. What's going on here? It's a little art trick. So a matrix in R, what is it? It's a vector containing concatenated columns. And then how does it know to treat it as a matrix, not a long vector? It has a dim attribute. Right, and then if you set dim to null, that kind of turns the matrix into a vector. You convert the matrix into this vector. Okay, and now we can look at the data, and well, with a little sense of history, these data only run up to 2016, I think. So the last big spike was from the unemployment in the Great Recession, peaking around 2009, 2010, and then you can see other historical episodes, the recession after 2001, a substantial recession in the 1980s with high unemployment, and so on. So we see seasonal variation. It's not even so easy to see the seasonal variation. It corresponds to little spikes each year, but you can hardly tell that from looking at it at this scale that they're at the same point of time in each year. And then you can maybe see a slower trend, perhaps business cycles on top. And well, just from this, maybe we can imagine that we can see seasonal variation, that these little cycles on top of all the other patterns maybe vary inflation by around 1 percentage point. Well, many times when people want to look at unemployment, they also look at the seasonally adjusted version, where they use the adjustment provided by the Bureau of Labor Statistics. And here I've downloaded that as well and plotted it in red. And you can see that the seasonally adjusted data basically are the same, except for not having those kind of high frequency wiggles each year. Whenever somebody doesn't give you the raw data, but they give you some processed version of it, you can wonder how they processed it. We probably more or less trust Bureau of Labor Statistics to do a decent job of time series analysis, but we can just see maybe whether their procedure has any artifacts that a careful statistician should be aware of. Or anyway, let's look into that. A way to look at what seasonal adjustment has done is to see how it affects the periodogram of the data, the frequencies in the data. And as we saw in the previous chapter, we're going to want to smooth the periodogram to estimate the frequencies present. And so here's some code to do that, and an extra useful trick for coding with time series in R, here we're using the TS class, the time series class, which helps R do some things automatically with, for instance, the frequency units. So here where U1 is the unadjusted data, U2 is the adjusted data, and we make them both into time series and just plot the two spectra. And here's what we get. Here I haven't put on the units of frequency, but so the units of frequency here should be cycles per year. And that makes sense because the highest frequency you can detect in the data is half a cycle per observation. That's a half a cycle per 12 months, which is 6 cycles per year. Half a cycle for each per month, which is 6 cycles per year. Okay. If you are writing a report, you would add the units here. Here I'm just looking at the raw output as a kind of exercise in interpreting that. Another thing you might want to do if you're writing a report, sometimes R will give you extra details like the bandwidth in the periodogram plot. You have to decide whether you're going to learn to understand that or remove it. If you don't want to understand it and talk about it, you probably shouldn't present it. Now, one thing you may have noticed about this this periodogram for the unadjusted unemployment, it doesn't just have a peak at 1 cycle per year. It has peaks at 2, 3, 4, 5, 6 cycles per year. I'll just go back to that plot here so you can check up on it. And right, actually the peak at 2 cycles per year is almost as big as the peak at 1 cycle per year. So what's going on here is I have to learn to use that better. So if seasonality were perfectly sinusoidal, we would just have a peak at 1 cycle per year. So in non-sinusoidal periodicity has what's called, in sound, they're often called harmonics. At higher frequencies, okay, so sometimes that's fairly clear, like if you have the Christmas summer effect, that's probably why the 2 cycles per year has a fairly large peak. But the 3, 4, and 5 is just because there's some pattern that's not sinusoidal, and so it has to be, to describe it in terms of sines and cosines, we need these harmonics. Okay, so we should probably say something about what we've learned from comparing these smooth periodograms. Well, I think these show that the smoothing does roughly what we would expect in the frequency domain. So let's say as we anticipate the Bureau of Labor Statistics. Seasonal adjustment removes most of the signal at seasonal frequencies. Let's say, and little elsewhere. Okay. It's often convenient to take the ratio of these two spectra, and that's called the frequency response of the smoother. It tells us how much the smoother contracts or inflates the sine and cosine components at each frequency omega. And when people think of the frequency response, there's two parts to that, really. There's the change in amplitude, which is what we're looking at here, possibly a change in phase. It could, the smoother could shift power from sines to cosines. That would be a change in the phase. There's a nice property of linear time invariant transformations that they don't move power between frequencies. And in that case, they're characterized by their frequency response function, because the only thing they can do is grow or shrink the power at a frequency, or shift power between sines and cosines at a fixed frequency. Smoothers are linear and time invariant, at least approximately. And the way to see this is to think about what it means to be linear and time invariant, and think that that's something that you basically expect a smoother to have. So if you scale or shift the data, you expect the smooth estimate to have the same scale or shift. The last thing you need for additivity, for linearity, is that an operation is linear if the operation applied to the sum is the sum of applying the operation to each part. Now, if you have two time series and you want to smooth the sum, you think that had better be pretty similar to the sum of the smooth if your smoother is doing a good job. So smoothers are linear and time invariant, and therefore they have this nice property that they're characterized by the frequency response function. If we want to calculate a frequency response function, we need to dig a little bit inside the object that R produces when it generates a spectrum. So here, rather than using spectrum in the most common way just to generate the periodogram, perhaps the smooth periodogram, here we're going to tell it exactly not to do the plot, and we're going to save the output. And so then we'll see all the different components that that get calculated in this spectral calculation, and then we can pick out the parts we want. So here we're doing the spectrum of the union of two time series. ts.union is a new command we haven't seen before, but you can probably guess what it does. It takes two time series R objects and it turns them into a bivariate time series with the times matched up. Here the times for U1 and U2 are the same, so it's a simple matchup. And we can, when you apply spectrum, you get the spectrum for one and you get the spectrum for the other. You take the ratio at each frequency and you plot it, and you have a plot of the frequency response function for the smoother. And here we go. So, and this is another way of representing basically the same information we had when we plotted both of the spectra. This is just taking the ratio of those two lines and plotting that. And so it shows more or less the same thing, but we can just see a little bit more some things a little bit more clearly. So the frequency ratio here, it's natural to measure on the log scale. If you measure it on the natural scale, it looks a little bit crazy because it has 3 orders of magnitude odd variation. Let's say the seasonal adjustment three orders of magnitude. This is just looking at this distance here, about 3 units on a log 10 scale. From the signal seasonal frequencies. And then you can also see from this it does a good job of preserving low frequencies but adds noise at high frequencies. There's an interesting property of smoothers, and that applies also to seasonal adjustment, that if you want to do something nice and smooth in the time domain, it has to be jagged in the frequency domain and vice versa. So that's what we see here. Well, we'll continue with this in the second part.